So this lecture will be totally focusing on the topic like what are the hypotheses we need for studying the diffraction in crystals. So in diffraction experiment, um, let me plot the graph or the diagram. So in diffraction experiment, we have a crystal here. So we have a crystal. This is crystal, and we have the probe, which can be X-rays, neutrons, or electrons. Um, that is the incoming electromagnetic waves. So the incoming, let me draw. So this is a probe, which can be, this is a probe, which can be the X-rays or electron or neutrons. That is, we need beams of X-rays, electrons, and neutrons all going in the same direction, and we need a columnated beam, that is very narrow beam or focused beam of small diameter, which interacts with the crystal, and then the particle will be diffused in many directions in this fashion. Sorry. So the particle or the wave will be diffused in this fashion at some theta angle, okay, from the reference, and so in diffraction at this specific direction we have very high intensity. So basically we have a detector, we have a detector. So this is a detector, which is able to measure the intensity of X-rays of the wave. So the intensity of the wave is proportional to the square modulus of the electric field. That is, intensity of the wave is proportional. Intensity of wave is directly proportional to the square modulus of the electric field. So we measure this intensity as a function of all position. So basically as a function of this angle theta. So as the function of theta or phi, generally we measure the intensity as a function of direction after the interaction with a crystal. So what about particles? So how do you measure for particles? So for particles, we measure the number of particles versus direction. We will see the number of particles is like the intensity of the quantum wave function of the particles and is proportional to the square modulus of the wave function of the particle. So in case of particles, intensity is proportional to the wave function, square modulus of the wave function of the particles. So in typical diffraction experiment, we see that the intensity is generally zero, but have some peak values in this fashion. Suppose I'm plotting the graph. So on x-axis there is theta, that is direction, and on y-axis that is intensity curve. And the graph looks something like this peak values. So here we can see that in typical diffraction experiment, the intensity is generally zero, but we have some peak values here, like here, peak values are here at some value of theta. So the high peak value is due to, so this, so the high peak value, so the high peak value is due to the constructive constructive interference constructive interference between the atoms. So the probe must be monochromatic for X-rays, that is, it should be of the same wavelength. For particles, monochromatic means they should be all of same quantum wavelength, that is, with the same energy or same velocity. Now let's discuss the four basic hypotheses which will be used to study this problem. So the first hypothesis is that we will study elastic scattering. We will study elastic scattering, which means that after the interaction with a crystal, the X-rays has the same wavelength, or the electrons have same energy. That is after scattering. That is after the interaction with the crystal. That is after the interaction with the crystal, the X-rays has the same wavelength after going diffraction, and or in case of particles like electrons or neutrons, um, they have same energy after scattering. So how do you represent the incident beam of X-rays? So the question is, how do you represent how do you represent the incident beam of X-rays? If they are monochromatic, so we can represent by a plane wave. So it is represented by a plane wave. Basically, we will use the exponential form. Let's consider the electric field in the X-ray as electromagnetic wave, and we can write it as in the form of this one. E equal to E naught E I K I R minus omega t. So this is the general expression for plane wave. So here Here EIE is the incident electromagnetic field, and KI here is the incident wave vector, which is perpendicular to the plane wave fronts. So it's in the direction of the propagation, while electromagnetic field is perpendicular to the incident wave vector, because it is a transverse wave. So um, let me represent it by a diagram. So this is our crystal. We have a probe here, that is X-rays or electrons or neutrons, and the direction of the incident wave vector is in this direction, that is KI. And we have diffraction here, at some theta angle, and we have the detector here. So we can write the modulus of the incident wave vector in the form of 2 pi by lambda. So frequency can be obtained by the relation of by this relation. So after the interaction with the crystal, if we measure what happens in some direction, we will have the wave going in the indicated direction. Suppose this is our so this is our so this is our so this is our crystal, and we have transverse waves, and the wave vector have this direction. This is KI, that is incident wave vector, and electric field is perpendicular to the direction of the wave vector, and this is the plane waves. So basically this is the plane waves, and when this plane waves interact with the crystal, we have um, scattered wave vector, that is diffraction, and we call it KS, the scattered wave vector. So after the interaction with the crystal, if we measure what happens in the some direction, let me write, this is scattered wave vector, this is scattered wave vector, this is incident wave vector. So we will have the wave going in the indicated direction with the wave vector Ks after the interaction with the crystal. So that is this scattered wave vector. we will see that the waves which comes out of crystal, that is this waves which is coming out of crystal, is overall this spherical wave. But if you go very far for the front of the spherical wave, that wave can be approximated with a plane wave. So here elastic means the modulus of the incident is equal to the modulus of scatter. That is, sorry, that is modulus of the incident wave vector is equal to the modulus of the scattered wave vector if we are considering the elastic scattering. It is equal to 2 pi by lambda. So the wavelength doesn't change, and we will call it just as k, that is the wave vector. So the wave keeps its wavelength. So if you think the electromagnetic wave from quantum point of view, we know that the energy of the waves is made of small packets of energy called photons, which is given by the equation E of photon is equal to Planck's constant upon frequency multiplied by frequency. So the elastic scattering means the wavelength doesn't change, frequency doesn't change. So the energy of photon does not change. So overall meaning that during elastic scattering, the energy doesn't change. So we can also have the inelastic scattering. So we can have inelastic scattering. Um, so when electromagnetic wave is instant on the crystal, that is some of the waves change their wavelength, we don't care. So if we measure the inelastic scattering, we get the vibrational measure information of the atoms. So if you measure the elastic scattering, we get the information of the position of atoms. Let me write. So if we measure the elastic scattering, we get the information of the position of atoms. So the next question is what is the meaning for elastic for particles? What is the meaning for elastic for particles? So if we send particles, we have free particles moving with some energy. So for a free particle, the wave function is given by the plane wave, that is psi equal to, this is the A is the amplitude, and here it is the reference of the plane wave, kr minus omega t. So what is different in this case? The meaning of the wave vector. We know that in quantum physics, the energy of particles um, is given by equal to modulus of p square by 2m, and in quantum physics we give the momentum by this expression, that is, so this is the expression for the momentum in the quantum physics. So substituting the value of the momentum in the energy equation, we are going to get energy as h square k square mod divided by 2m. So here the Planck's constant is constant, so we take outside the value of h square. So here we are going to get k square by 2m, and the de Broglie wavelength is given by this equation, that is 2 pi by k vector, that is, so this is de Broglie wavelength, so this is de Broglie wavelength, and we can write this expression in the form of this also, that is h cross p momentum. So here we can think of h cross equal to h by 2 pi. So the elastic means the energy do not change. So the elastic means the energy do not change, So modulus of the wave vector, so modulus of the wave vector that is k do not change. So we can write the as per energy equation. So as per energy equation we can write this expression. So that is sorry. So we can write equal to p square by 2m, p is equal to hk, h cross k, that is h is constant here, so this is the incident wave vector k square by 2m, which is equal to the scattered wave vector here k square by 2m. So the electron change direction but does not lose energy. This means that the electron change the direction but it doesn't lose energy, and also the Broglie wavelength remains constant. So this is our first hypothesis for studying the diffraction in crystals. Now moving to the second hypothesis. This is our second hypothesis, that we will study the scattering in the far field approximation, that is far field approximation. That is, we will deal with the far field approximation. That it means that let me plot. So this is a crystal, and this is the, suppose this is the diameter of the crystal, and we are sending some waves here, and this is the incident wave, and this is the diffracted wave, and we have a detector locating here at r distance. This is r distance. So from the crystal, the detector is located at r distance. Okay. This is the detector. So it means that, so far field approximation means that you send the X-rays or electrons, and the typical size of crystal, let's call it as D, and then we put our detector at a distance R from the crystal. So we are measuring the intensity of the wave or number of particles at a distance R vector, such that the distance R is very greater than the size of the crystal. So that is, the distance is much larger than the size of the crystal. That is, distance is much larger than the size of crystal. So this approximation is much more important for mathematical deployment. So we can call that R by D is greater than 1. Now coming to the third approximation. So the third approximation, we will use the Born approximation. Born approximation. Born approximation of scattering. Born approximation of scattering, which means that the first order approximation, we consider only one interaction between the X-ray wave and the crystal, or between the electron or neutron and the crystal. It means that we don't consider the multiple scattering. Let me write that it means that we consider only the first order approximation. We consider only one interaction between the X-ray wave and the crystal, or between the electron or neutron and the crystal It means that overall sense that we don't consider multiple scattering. Now coming to the last hypothesis. That is hypothesis 4. We don't consider small angles. We don't consider small angles. So we will use these 4 hypotheses for Von-Laue semi-empirical approach as well as the particle approach. So you should remember that the particle approach is only used for the case of particles like electrons and neutrons, and the Von-Laue approach is used for the case of X-ray waves. So let me give you some overview of the Von-Laue approach, which will be the topic of our next discussion in next lecture. So in Von-Laue approach, we have an incident electromagnetic wave with electric field and amplitude E0, and it's represented by this equation, that is incident electromagnetic wave EI equal to E0 exponential EI KI R minus omega t That is, this is the instant wave vector ki. Now further simplifying it, we are going to get E naught ei ki r multiplied by e minus omega t. So we have elastic scattering by the first hypothesis. So the frequency doesn't change. That is omega equal to 2 pi ev doesn't change. So we will not write. So we will not consider this expression that this is constant. This is constant thing. So we will not consider this expression because it's constant, because the frequency is constant. So we will consider only this equation, that is ei equal to E naught e ki r. This is I. So we will consider only this approximation. So we can write. The instant wave vector, the modulus of the instant wave vector as 2 pi by lambda. So so the overall approach is that we have atom here, we have some atom here, and we have the electromagnetic wave arriving at this atom, position of atom. The electric field direction is perpendicular to this direction, and the direction of the wave vector is this one. So basically a wave arrives the so this is the direction of the represented ei, and this electromagnetic wave hits the atom, which puts this around the electrons of an atom in oscillation in this fashion. So the electrons of this atom goes under oscillation when the atom is get hit by this wave. So it will lead to the oscillating dipole, which generate the emission of waves in this fashion, spherical waves. So the oscillating dipole will result in the spherical wave generation. And we know that when we go far from the oscillating dipoles of waves, which are almost spherical waves, so these are spherical waves generated by the heating of electromagnetic waves to the electrons. So basically we will use hypothesis 2, that is far field approximation. Now we will study more about the Moll-Laue approach in the next lecture. So for now, thank you.